Okay, so in this session, we will quickly go through Lab 0, like how to set up Vivado project and into the details of Lab 0. And I'll also start explaining Lab 1 after Lab 0. So just to start with, okay, feel free to stop me if you have any doubts in any time. So we'll start a new project. So these are the steps that you need to follow. Like you can just click on next, uh, give any name and choose a location. So it's just an RTL project. You can skip this for now and add the files later. So this is one thing that is important. You need to select the device. So that is as per. So this is the device XC7Z010. This one. So for all the projects in this course, you need to select the same device when you're creating a new Vivado project. And then you can just click on finish. So after creating the project, you have to have, for every project, you need two files. One is the source file containing all the source logic, and another one is the test bench that we'll be using to provide inputs. So first, to create a design source, click on add source. So add on create design source. So you can just give a source, this one, and then just finish. So you can just skip it for now. So this is the source file that's created, and another one is you're supposed to create a test bench. Okay. You can just skip these things for now. So make sure that your test bench is set as top in your simulation sources. So this test bench should be the top. So for lab, just using the code that is provided for lab 0. I'll just explain it in a bit. So for lab 0, if you see, we are going to create a 7-segment display using the state diagram and the inputs provided here. So basically we have two modules. One is the DFF and the counter module. So the logic for these two modules should be written inside your source. So inside your source file, and the test bench is basically used to provide the inputs. Like so for these two modules, the inputs are clear, clock, and view. These will be provided from the test bench. So there is some disturbance. If someone wants, I think someone is please mute yourself. Okay, so these are the two modules, and so the logic for these two modules is if you say, let me just take you to the, so you have your clear, clock, and view. So clear is initially set to 0, then it is set to 1. The clock is something which keeps on changing every 1 nanosecond, and then you have your u, which is like 1 for some time, and then it is set to 0. So these are the inputs uh, for our module. Now, if you see the DFF module, you have the next state and the clear bit. So if clear is set to 1, then our Q, the output of the DFF module will be the next state. So that is mentioned over here. So if you see the DFF block, you have an always block. So we always perform operations on the positive edge of the clock cycle. During negative edge, we don't do anything. So we enter this block only during the positive edge of the clock cycle. So that is what is mentioned over here. The inputs for this DFF block are the next state, clear, and clock. So these are mentioned by the inputs, and the output is going to be Q, which is mentioned over here. So the output is also written as register because it is modified inside our always block. So in general Verilog, if you are using any variable and if you are modifying a variable inside always block, you need to you need to declare it as a register. So that is the logic. Now, so if your clear bit is set to 1, your Q should be next state, and if your clear is set to 0, then you have to set it to uh, 0. That means you are resetting everything, and it should be set to 0. Now, if we see the counter module, so the counter module also has Q as its input. Then it has U, which is provided from the test bench, and then you have next state, which is our output. We have A, B, C, D, E, F, G, which are this display. So the signals for the 7-segment display. So those are all as well declared as output registers. Now, if you see in the state diagram, so we have like six states. If u is set to 1, we keep on moving forward, like from 0 we go to 1, 1 to 2, 3, 4, 5, and once we reach 5, and if u is 1, we again have to go to 0. So if u is 1 and if our current state is 5, we go to 0. So that is what is mentioned in this block. Else, if u is 1 and if you are in any other state other than 5, we have to just increment it by 1. So this is the case for u is equal to 1. Now if u is 0, then we have to decrement. Like if we are in 5, we have to go to 4, 3, 2, 1, 0, and if we are at 0, we have to change it to 5. So that is the logic that is explained over here. Just subtract -1 if u is 0, that is decrementing, and if the current state is 0, we have to just move to 5. So these are the two logics. After that, so now we have our queue ready. So now we have to just so depending on whether it is 0, 1, 2, 3, 4, 5, we have to just set these values. So whether it is 1 or we have to set, so if it is 1, we have to just set B and C to 1, and all the other values must be set to 0. Yeah, I think there is okay. So you just refer to this diagram and set these things accordingly. Now, if we go to the test bench, as already mentioned, we just have 3 inputs. So these are the values that we are modifying in our test bench. So they are declared as registers. And all other values are just outputs from the source code. So they are just declared as wires. Then we are supposed to call the two modules that we have written, DFF3 and counter. So this is like a variable name. It can be anything, and this is the class, the module name. This has to be the same, and you are supposed to so the order in which you have declared things here, so the same order must be used while passing the values, passing the variables, and calling these functions. So you should strictly follow the same order. Mm, so as per the this diagram, you have to set your clear to 0 initially and clock to 1, and you should be set to 1. After 1 nanosecond, your clear will be set to 1, and your after 16 nanoseconds, your u will be set to 0. So this is one thing, and the clock is always changing after each 1 nanosecond. It's changing to 1 and 0, so that is written in the always block. This should happen all the time. And here we have, so when you create the test bench module, test bench file itself, this will be written, the time scale will be already written, so don't change this one. So this is 1 nanosecond. Now, so this is the mapping from the PDF to the code, and I'll try to run this one. So once you are done with your code, you have to submit a report, and so it should have your name, class, and the email ID or something, and then you are supposed to copy paste your all the code that you have written, source code, test bench. Then you should keep you should have screenshots of your waveform. Okay, I'll explain. So we have run the simulation. After running the simulation, so this is the waveform. So you can use this button to move to the start of the simulation, and so this is, and you can use the minimize to visualize them properly. So these are a clock clear u, and so it is. So initially our u is set to 1, so it is incrementing 0 1 0 1 2 3 4 5. Then we have then from here, so at this position our u is changed to 0. So from there, that point onwards, we are decrementing the value, so 2 1 0 0 5 and so on. So this is how it works. And if you so these this panel shows you all the inputs and outputs. You can also change I think now, so there will be a radix option if you have if your inputs are in hexadecimal or hexadecimal, you can change it to decimal, octal, and so on. I think for the next projects that will be useful. And another thing is, so when you run the simulation, you get the full output. But if you want to debug or something, and if you want to understand what's happening, you can just restart. So restart it, it's not, there is nothing empty. Then you can set it to 1 nanosecond, and you can click on this one. So in this way, you can understand what is happening, whether your code is correct or not. So you have to place these screenshots in your report, simulation screenshots. Then you have to run the synthesis. This might take some time. So we can just click on open synthesized design. So as you have to place the screenshots of IO planning and floor planning. So here, if you see, this is the floor planning. Just zoom in and take a screenshot, and then go to IO planning. Take a screenshot and place it in your report. So when you're so for any project, for any order project submission, you you have to zip the entire Verilog project and the report and just upload it into your Canvas. So that is with respect to lab 0 and general submission details. Do you have any doubts? Okay. So now I'll go to lab 1. So lab 1, so we have to implement a restoring division logic in lab 1. So basically, okay. So basically, you will have a dividend and a divisor provided using the, and you have to output the quotient and the remainder. For that, you have to use the restoring logic. So how it works, so if you see this diagram, we'll have so the entire project can be written in just one module. So in the previous lab 0, we have two modules, DFF and counter. For this project, for division, this project, you can just have one whole module in your source file. So the logic here is, so these are, so I just converted these paragraphs into points. We can understand this using this. So we'll have three registers: register B, register R, and register Q. So this is so the register B, register R, and register Q. Q and R for quotient and remainder. So initially, what we would do is the A that is given to us, we will assign that A value to our register Q, and then we have a subtractor module. So what subtract? So the subtractor module takes the partial remainder and subtracts B from it. So what is the partial remainder? So the partial remainder is register R. Okay. So in order to understand these diagrams, just keenly follow these lines. So if you see these lines are coming from this register R module. So we take all these things. So register R is 16-bit. So 0 to 15 of that, and we take 1 bit from register Q. That is the last, the most significant bit, 31st bit. So this is one input to the subtraction module, and the other input is your B. So B is also 0 to 15. It is a 16-bit number, and we are appending 10 at the most significant bit. So in this in the subtraction module, you are taking register RQ31. From this we are subtracting our B value. So this is with respect to subtraction. Now once you get an output, we will see the most significant bit of the output. If the most significant bit of the output is 0, so this is the most significant bit which is given to the multiplexer. So depending on if it is 0 or not, so if it is 0 or not, we will have different outputs from the multiplexer. So one of the input to the multiplexer is your register R. So register R0 to 14 and Q31. So if you see these lines, we are taking this Q31 into this multiplexer, and the remaining bits are 0 to 14. The 15th bit is neglected. Register R 15th bit is not given to the multiplexer. It's 0 to 14 with a Q31. And the another input to your multiplexer is subtraction, the output from the subtraction module, that is 0 to 15. I hope this is clear. So we have two inputs, which each one of them is 16-bit. Depending on the subtraction output, if it is 0, we'll select one of them. If it is 1, we'll select another one. So if the result of the subtraction is negative, the multiplexer will select this one. If it is positive, the multiplexer will select the subtraction output. So this will be your register R. This is how you assign value to your register R. And then for the register Q, you'll have 0 to 30 of your queue, and the 0th bit, the least significant bit, is nothing but the negation of the sub output most significant bit. So okay, one bit of Q is obtained from the sign bit of the subtractor result and returned to the LSB of register Q. So this is the sign bit, the most significant bit. This is negated and it is set as Q of 0. So this will become the 32 bit Q. So I just converted this paragraph into this point. That's all. So first we'll assign A to register Q, B is B, and register R is 0. Then we will do a left shift. So left shift is nothing but taking one bit from the removing the most significant bit from Q. So these values are given to the subtraction module, and we subtract B from it. So the output from the subtraction module is used to decide what should be the mux output and what should be assigned to our register R. And it is also used to set the least significant bit of Q. So this is the crux of this one. When you come to the so your test pen should have clear start clock A and B. So these are our inputs. Clear start clock AB are the inputs, and QR are the outputs, and busy ready count are also they are not final outputs, but they are just used internally, so you can display them as well. So so this paragraph I try to explain it over here, or here I'll go through it. So start signal, so if your start signal is set to 1, that means you're supposed to start the division. The busy busy ready are something which we have to set in our source code. So depending on clear and start values, if clear is 0, your busy is 0 and ready is 0. If clear is set to 1 and if your start is also 1, then you have to start your division. That means the module is busy now, so you have to set it to 1, and ready is 0. So ready here indicates whether your the outputs are ready or not. Is the division completed or not is specified by the ready variable. So once your busy is set to 1, we have to start performing the division, and so we need to keep iterating. We have to do these steps for 32 times. So our uh, so it's just the length of our A. So we have to do that 32 times. So to keep track of that, how many times we have performed it, we use this count variable. So once this count variable reaches 32, we set our busy to 0. That means the division is over, and we set our ready to I'm sorry. We set our ready to 1. So the outputs are ready. Now you can check the outputs once the ready becomes 1. So Q and R are ready. So this is the uh, uh, this is how you are supposed to use these variables and perform division. So the report submission and other stuffs remain same. We have to use the same the device number. You have to take screenshots of your simulation. So the synthesis, IO planning, and floor planning. So along with your Verilog code, you are supposed to place all this in your report. So if anyone have doubts regarding this restoring division, you can. So is everyone clear with the restoring division part? So that is what you are supposed to do for lab 1. So that's all I have for this session. If you have any doubts regarding like general Verilog or Lab 0, Lab 1, you can feel free to ask.
We don't have to submit lab 0, 0, right?
No, you don't have to submit Lab 0.
All right, thanks.
Yeah.
Can I ask about like lab during office hour, because I am still not familiarized with Verilog yet. So if I have any issue when trying to do the lab, can I go to office hour and ask?
Okay. Yeah, sure. You can.
Share my screen to make sure that tutorial to how to use mask, because like I have downloaded.
Urvi, can you please mute yourself? So here, yeah, you can join any of the TS office hours and ask queries regarding lab any point of time.
Okay, thank you.